Hello, I would like to kind of recap the Avrami equation and related phase transformation to Avrami formula. First of all, the general form is very simple. Y equal to 1 minus e to the power minus k t to the power n. If you plot this, giving k and n are constant and t could be per seconds or per minute depending on the k and n, this would be any of these shapes, like a S shape. Avrami equation always has this kind of S shape. It's related to the speed of a reaction. So at the beginning it goes slow, then right away goes up fast, and toward the final stages it becomes a little bit tapered off. So this is a simple mathematic drawing. But then it comes to material science, you have to pay attention first of all, what is the reaction? Is the reaction annealing? So you know that when you have a material and your material subjected to some cold work, it becomes a little bit of work hardened, and if you want to release the stress, you put it in a furnace. You can put it at 200, 250 or 300 degrees Celsius. You know that annealing, the higher the temperature is, the reaction happens faster, the dislocation would be kind of tangled, and now there would be release and unlock at a higher temperature faster. So if you write something about the Avrami equation for this particular situation, you realize the lower the temperature is, the longer time required for the reaction to be completed. And I intentionally give two different kind of scales. Usually this is in ln or log. And it could be start from 0, 110 or start from 110 or whatever this is given based on these two values and the reaction. So for every particular temperature, you might have different K and N obviously, and of course the nature of the reaction. Moreover, if your reaction is something like a eutectoid, it means that you have a 727, you reduce the temperature, your austenite become ferrite and cementite in form of lamellar shape of perlite. The lower the temperature, faster the reaction is, exactly the opposite. So in this case, the higher the temperature, longer it takes for the reaction to be completed. So this is, first you have to understand what reaction you are talking, what is the effect of temperature on that reaction. But this is free from temperature because these N and K are given for particular temperature and calculated. So mostly we talk about eutectoid phase transformation, in which you have austenite become ferrite plus cementite. This happens at 727 roughly. And if this happens in form of lamellar structure, it's called perlite. So we're talking about this reaction, for example. Higher the temperature, retarding this reaction. If I go at 727, it would be 0. Nothing happens because it's just about for the reaction to happen. Now, I like to play a little bit with this equation, some mathematical calculation, and then we can talk more. So now let's just maybe right here. So I would modify this equation. So if I modify the equation, and by the way, this value is obviously, this value has to be between 0 to 1, because this is never more than 1. This term at very, very lowest is 0, and this becomes 1. At the very, very highest is 1, and this becomes 0. So y is always between 0 to 1. It's never more than 1. Meaning you cannot have more than 100% of the reaction to be complete. That's observation 1. Observation 2, I want to discuss the effect of n and k with a few examples. Well, let me modify this in a very simple way. So what I have here, I don't write the equation again, but I do a ln from both sides. I'll bring that one multiply by negative, and this would be minus k t to the power n. Maybe I delete this part so we know all about the actual eutectoid phase transformation, so we don't need this here. So here, and you can do a little better than that. So from here I can write here, so I affect the negative and it becomes ln of 1 divided by 1 minus 1 k to the t to the power n. Do another ln from this, and that would be the ln of ln k plus n t. Oh, sorry, n ln t. Sorry, n ln t. Well, it seems to be more confusing, but in fact, this, if you just put it in a simple perspective, so this I call it y, and this I call it x, and I call this one a, and n is the same as n. So what I have here is, this is y is equal to a plus n x. X. Obviously, this is the equation of a simple straight line. So if I want to write it like in an easier way, so I just draw the plotted here. Maybe I just do it here. So this would be something like this. So obviously it's going to be a simple line. The slope of the line, tangent alpha is n, and simply if I have 2 points only, I need 2 points, this point and this point, to calculate n. So if I give you the time required for 50% of the reaction to be completed in one scenario, and then I give another one time required for 75% to be completed, another one, so you have simply 2 points. You can make a line on this simple equation. Both n and k can be completed. So this is as far as the Avrami equation is concerned. You might say, well, this is way too complex. It is not. It's very simple. And in fact, when I put this one, let's say 0.5, so it's very simple. It's become ln 1 divided by 0.5, ln 2. You know what is the ln 2. You know what is the ln of ln 2, and the reaction would be very simple. So use any of these 3 equations, depends on the scenario. So if I have y and I want to calculate n, maybe that's the best. Again, let's say y is 0.1 or 0.9. So 0.9, this becomes 10. Ln of the 10, you have it. Ln of the 10 you have. Then you have the k, you have the n, you calculate t in one line. But if you have, for example, t and n and k, so why not use this equation? And directly you can calculate the values, whatever needed, in this case, y. So I want to give a few examples, and then we do it, generalize the effect of n and k. So let's start with an example here. Assuming my n is equal to 4 and the k value is equal to 6.7 10 to the minus 5. Let's also add that the time is 10 seconds, assuming they're all with the same equation. The question is asking, in 10 seconds, if n is 4 and k is 6.7 10 to the minus 5, how much of the reaction, how many percent of reaction has been completed? So simply we can go and calculate that. The calculation is very simple. So you want to find this value, right? So in this case, I use the second one, which is easier. I put here ln of, or you can actually use the same one. It doesn't matter. I do ln of 1 minus y is equal to minus k t to the power n. So just let's plug it in, very simple. I'm just going to doing it right at the spot. So this value, so we want to calculate this value here first, is equal to ln 1 minus y is equal to minus 6.7 10 to the minus 5 10 seconds to the power 4. Let's do a simple calculation here. I'll just do it right in the spot. So here, so we have 6.7 10 to the minus 5 multiplied by 10,000. So this value becomes 6 minus 10 to the minus 1. And now I want to solve this. So obviously I can do the e of both sides. So 1 minus y is equal to the ln of this value, the e of the value, e to the power minus 6.7 10 to the minus 1. So here, negative of this value, so e to the power minus 0.67 and this value from here, so you can simplify, this value becomes 0.511 and y is equal to 0.4883. I would say roughly around 0.49, or 49% of the reaction is completed. Well, it's kind of ironic. It's almost half the reaction is completed. What if the question is asking, calculate the reaction rate? So what is the reaction rate? The reaction rate is 1 divided by t.5. Means 1 divided by the time required for 50% of the reaction to be completed. 49, so I can't just make a judgment here. Let's do it one time for 0.5. So in this case, I want to calculate how long it takes for 50% to be completed. I assume if it takes 10 seconds for 49%, should takes a little longer. I don't know, 1, 2.5 seconds longer. But let's experience this here. So in this time I do having this y, so I use again this equation, so it's going to be 0.5 k t to the power, and maybe I just replace the values here for just avoid writing longer. So minus 6.7 10 to the minus 5 t unknown to the power 4. Okay, so from here, let's see what's going to happen here. So I need to calculate t. T is equal to ln 0.5 divided by minus 6.7 10 to the minus 5, and this to the power 1/4. I can simply calculate here now, just right on the spot again. Ln 0.5 divided by minus 6.7 10 to the minus 5. So this value becomes 10,345, and then I'm going to go and I'm going to find the value. So here is interesting. This t become or 10.1 seconds, roughly. It's 8.5 or like 8.5. So only 0.1 second later, it's kind of, I should have known. I mean, it seems like it gives me that signal that a little longer. Yeah, that makes sense. If you calculate this and this become 9 seconds, you soon we got the problem again. So this means it would have been 9 seconds is wrong. But now it sounds good. So this is correct. So now what is the reaction rate? The reaction rate is here. So then it's going to be the reaction rate for this reaction is 1 divided by 10, 1. And this value is roughly around 0.0992. That's what we have here. So very simple. It doesn't matter how I change it in exam. There will be a question similar to this to exam. I have to make sure you understand it. It will be maybe 10 marks or 5 marks. So, but it takes about a few minutes only to finish this. Now let's just play a little bit with these values here. I'm just going to remember this values here, 10 and so on, and the reaction rate. I'm going to play a little bit here, and I'm going to just go here. Look at what I'm going to do. I'm going to increase the n by 25%. 25% of 4, so become 5. I'm going to increase this by 400%. Decrease this by 400%. Means 4 times less. So 6.7 10 to minus 5 divided by 4. So this become the new it's going to be 1.75 10 to the minus 6. I want to see what is your feeling now. I reduce this by 400%. I increase n by 25%. This shows the effect of which is more predominant, with the effect of which one is it's more dominant here. So let me just delete these one here, and I'm just going to find the time required for 50% of the new one. And my feeling says, so because this equation here, t is to the power n, the effect of n is much more. And we talk about this in a lecture. Lectures also, we showed lots of graphs. This should be the reality, but I want to see mathematically if this is actually will be proven here. So I simply work this out. By the way, erasing this, it takes much more effort, so I don't need to go to gym today anymore. Not that I do actually, but anyway, so done. So let's do the same thing here. So remember that what we had ln 1 minus 0.5 is equal to, remember that was k, so it was 6.7, minus 1.67, the new one. Let me just, minus 1.675, 10 to the minus 6, t to the power 5. Let's calculate how long it takes for 50% of this reaction to be completed. Same thing, ln 0.5 divided by minus 1.675, 10 to the minus 6 And now this to the power, so you do to the power, write this value here, 413. So okay, let me just, before this value from here, t to the power 5, or t, let's just do one shot. T is equal to 413,819.2 to the power 0.2, right? So let me do that here. So I write here 413,819. I just made this just on the spot, to the power 0.2. Interesting. So let me just see if this is correct. Power 0.2. I'm going to do one more time just to make sure this is correct. I don't want to make a mistake here. So ln 0.5 divided by, this is 400% smaller, this divided by 4. Okay, so it is divided by 1.675, 10 to the minus 6. That's correct. And then this to the power 413,819 to the power 0.2. That's correct. So from here, t is equal to 1328 seconds. You see now, that pretty much says it. So I increased this only 25%. I reduced this 400%, but still the time used to be 10.1. Now it's about a little bit longer. I promise, or I bet that if I would have reduced this by 300%, it would have been the same. That itself shows the effect of N is much more important, impactful than the effect of K. And we mentioned that you go 1 unit here, maybe you have to reduce this by 10 folds. And we saw that the graph we had. So that's as far as the Avrami equation is concerned. Just feel very comfortable with this, the formula of the reaction. Don't forget, this is only between 0 to 1. Is a percentage, as 0 is 0%, 1 means 100%. Obviously, this cannot be ever more than 1, cannot be less than 0. So the range of variation of the range is between 0 to 1. People asking about the second or minute, that is defined by this K and N. So if you change the K and N, obviously it changes the value. So if it's by N and K are for seconds, you get the seconds. If the question says per minute, it's per minute. In fact, I can even give you per second, ask what is per minute, it's going to be different, obviously. So that logarithm. One last thing as far as this is concerned, and I know I mention it often in my class, but you should feel very comfortable to be able to read a log scale. There are a couple of kinds of log scales. One is when you see something like this, 0, 1, 10, and so on. So you will see it's a linear, this equal to this. So I said that if you really want to, in a real life, and the exam as well, if you really get some value right here, and you want to know what is this, how much is this, the easiest way to do is, well, this is 1, correct? What does 1 mean? 1 means 10 to the power 0. So then you go and measure in real life. You measure this distance. Let's say, for the sake of argument, is 30 millimeter. I'm just measuring this distance. And then you measure this distance is 6 millimeters. I'm just saying that. Okay, then where this is obviously 1 divided by 5, right? 6 divided by 30. So This value, remember that? So if you want to find what is this length from here to here, all you do is you do 10 to the power 0.2. 10 to this, how far it is, then you can calculate. So 10 divided by 10 to the power 0.2, or obviously the 10 square root of that is, this would be 3.16, whatever unit is. So this is 3.16. So it used to be 1 here. It looks like a larger, you can say, well, yeah, but yeah, because it's a log or ln. So this is the nature of that. So this is one way to read. If I want to calculate, for example, and unfortunately I can't go that far, somewhere around here, and here is 0.8 of the whole thing, then guess what? You see these things here? So this used to be 0, right? So 0 means that this is none, this is 1. So this should be between these two. And you go and simply calculate. So in order to calculate this one, you use the same. You measure this, and you do this divided by this. And in that case, you do the ln of that value or the log of that value. So that is how you actually measure the ln. Doesn't matter in X or Y. And always, so you have to have that feeling that always it looks like when it's half, its value is less than half. So for example, if I'm halfway here, so it would be 10 to the power 0.5. So actually, you know what, I think I made a mistake here. This is wrong, sorry about that. This thing is 10 to the power, let me see that, 10 to the power 0.2, sorry, this is 1.58, that's this. If it would have been half, would have been 10 to the power 0.5, would have been 3.16, whatever. So you can see when it looks like half is only 3.1, it's not between 1 and 10 is 5, that's not going to work. So you always go the ratio. So this is 6 millimeter, the whole thing is 30 millimeter. This is 1/5 of the whole thing, but the value is less than 0.2. You see, it's 1.58. So that's how you calculate this, regardless of its ln. And then there's another way, there's another system, and that looks like, let me delete this. This looks like this. That looks like you have it like this, and itself it looks like this, and this itself has been already used this. So this is, for example, is 10, 20, 30, 40, and so on. If this is the case, it makes it a little harder to read. So, but this has already been calculated. If you have given this one here, the best way is to try to, there are some rulers, that is a ln or log rulers, you use that. But in that case, this has already been affected by the fact this is ln. You make the best guess. If this is the case, usually you should have bang on, like this is 40 right there. So it's hard to calculate this guy here halfway through, because it's not exactly halfway, but this is already has the impact. Or just go from here 10, this shows 100, forget about this ln, and you do the same thing. You find value, for example, here, I'm just going to bring it down here just because you can be able to see it. So imagine that this is 100 here. So you want to find the value around this point. You know, it's roughly around 30 to 40, but forget about that. You just do the calculation. You measure this length. You know, this is 1, this is 2. You measure the length, you will say that whatever the value is, you know, and then, like for example, you can see that this seems to be, for example, 0.56 of the whole thing. Therefore, this value here is 1, this is 10 to the power 1, this is 10 to the power 2, therefore that value would be 10 to the power 1.56. I'm just saying that, for example, whatever the value is, most probably is not that one, but 10 to the power 1.56 would be so let me see that 10 to the power 1.46, something around that, like 60 something, because 10 to the power 2 is 100, so 10 to the power 1.56 in this case would be about 36 point something, which is correct. Either way you can calculate that. So I really hope that this explains the log and ln. So again, that was the mistake, is 10 to the power 0.2. I mentioned 10 to the power 5. This one, it is halfway. Just a simple measurement will do. Okay, so, and this will kind of conclude our discussion about the Avrami and log and ln. So now I want to talk a little bit about the phase diagram and the TT diagram for a very short time, and hopefully that covers some ambiguity it comes with the TTT diagram. So this is a general form or a schematic form of the TTT diagram for one particular alloy. By the way, this alloy is at the eutectoid because we don't have any primary phase. So here, temperature, here, time, log per second. So here are some regions here. We have austenite here, stable austenite. Then we have unstable austenite, obviously because I can stop the time. If I'm at this point, I have to, maybe for 1 second I'm here, for 1,000 seconds I have to go this way. And then we have perlite in this region. Then we have bainite in this region, and we have martensite. So now the question is, I'm talking about the isothermal, which is easy, and then we talk about a little more complex later on in lecture, which is continuous cooling. In real life, we do continuous cooling, means I go, for example, I'm just gonna not mess up with this, I go like this. It's continuous cooling, but I'm not gonna do it now. So let's understand the concept behind this and deal with isothermal, and then later on we can talk about actually continuous cooling, which relatively is more complex. So imagine I'm going to start with a simple sample. I'm at this point here above the eutectoid temperature, 800 degrees, let's say from here, 800, fully austenized. Then I drop it down to, let's say, 600. I come like this to 600. And then, and again, I'm sure this is not completely the same as the one in the textbook, but I'm just working based on this. And these are second, 1, 10, 100, and you can see that 1,000 and 10,000. So you maybe don't see that lower part. I'm gonna go quickly to here. This is the time. So I'm gonna go again to close. So I bring it down to 600, and then I give plenty of time. When I say plenty of time, let's say I give 1,000 seconds. I'm not gonna make it because I don't wanna mess up. I'm here, 1,000 seconds. What structure do I have? Because I passed this one, which is the perlite finish, I have 100% perlite. But what if I go up to here? I go roughly around whatever time is, let's say 30 seconds. And then at this, theoretically it's very easy, but in practice we have to change the medium right away. Right away, I drop the temperature to 300. And then I give let's about maybe 2000 seconds. So first at 800, then I go, maybe I just go closer here because I don't want to go to the wide shot. So here, at 800, I am plenty of time. I drop the temperature to 600 and I give this much time, which is roughly, I would say maybe 30 seconds. 30 seconds. Then I bring it to 300 degree. Maybe I use a different color just to 300 degree. And I give 2000 seconds. And then at this point, after 2000, I drop it suddenly to room temperature. Okay? I want to know what is my structure. So let's follow this. Well, 100% here, and now I have to go. So in here, 100% I have austenite. 100% austenite. You bring it to 600 for this amount of time. You meet right at 50% perlite. So you get 50% perlite and 50% austenite. This is unstable austenite. You can't hang on there. It has to do something. So this is at this stage. Call it point A. Then I go to point B. I bring it to 300, give 3000 seconds. So, or 2000 seconds. So I have 50% unstable austenite, as if I start fresh austenite from here. It would have been the same thing if I bring it all the way down and I give 2000 seconds. 50% of my whatever amount austenite I have, it forms to bainite. So this is out of picture. This is the currency span. 50% of that is 25% bainite and 25% still unstable austenite. And then I go to room temperature. So this is point B. So I go to point C. Whatever I have, excuse me, remains the same. The remaining 25% of austenite become martensite. This is a very unwanted structure because it has multiple constituency, different properties. It's fail as far as the ductility is concerned in martensite. It fail as far as strength is concerned on perlite. So it has two weakest link. So that's unwanted. But this is what we get here. The part that the students often have problem is why I don't go this much. Because this is the bainite start, this is the bainite 50%, this is the bainite finish. That's correct. But this is required to get to the point that the bainite phase transformation starts. So as this length is required, this length is required at 600 for the perlite transformation to be started. Yes, just to start, and then this long it takes to become 50%, and you add them together. If I ask you how long it takes for 100% austenite transform to perlite at 600, your answer is, you mean how long is the minimum? Because you can say 5 years, that works, but minimum time is this much, you see? Then you bring it down here, whatever is that, 80 seconds. 700, 500 seconds here. So this is the minimum. How long it takes for 100% bainite form at 300, assuming you come from 800 to this temperature, is this guy. You go here. This is the minimum time required at 300 for 100% austenite become 100% bainite. If I would have asked, okay, how long it takes, we go like this, this, how long it takes for preventing in this situation getting martensite, so you have 50%, so you go instead of whatever is that, you go further, your answer would be, oh, look at that now, so you want to finish all the unstable austenite to bainite, so you have 50% here austenite, but it doesn't matter, it takes this long, and that's 10,000 seconds, so you need 10,000 seconds. If this is the reaction you do, you go like this, you drop it, and at 300, how long it takes for the whole reaction to be completed, become all the austenite become bainite, then you will say, okay, so 30 seconds plus 10,000 seconds, it takes 10,030 seconds. When you go from 800 to 600, you give 30 seconds, you come down, you give 10,000 seconds, and in that case, in that case, your point D, whatever, D, so you have D, you have 50% perlite, 50% bainite. This is at 600 Celsius, this is at 300 Celsius. I hope that explains, and no matter how I play with this, it's gonna be that set. So when I say how long it takes, means minimum amount of time requires for this to be completed. And that is all you need to know for isothermal. It gets a little bit more sketchy when it comes to the continuous cooling, but first you have to understand this. I would offer another perhaps lightboard style lecture on the isothermal, but really this is important. Thank you very much.